second talk of the day. We have Miguel Montero from Harvard, who's going to tell us about Cobordisms, anomalies, and Swampland in 9 dimensions. Take it away, Miguel.
All right, thanks a lot, Cody. So I would like to start by thanking you and John for putting together this very nice series and for giving me the opportunity to present this work here. So I'm going to be talking about what happens when two things that I really like, Swampland and anomalies, get mixed together. And I hope you find the results as interesting as I do. So this being a Swampland talk, I will start at the starting point that many Swampland talks have, which is arguably the oldest and best known Swampland conjecture, which is the idea that in quantum gravity we should have no global symmetries. Now, I don't know who was the first who said this. So the reference keeps going back, and just yesterday I heard in a different talk that apparently this was said by Wheeler in the 50s. So I couldn't find the reference. Who knows? Anyway, it's a statement which has been around for a while, and we have lots of evidence for it. It's true in every string compactification. We have proofs in the worksheet and in ADS CFT. And so I think it's fair to say that we will all be very surprised if this thing turned out to not be correct. It would be a huge surprise. So that's nice. That's a Swampland statement which is very reliable. But unfortunately, when it comes to constraining low energy physics, which is what we want to do with the Swampland in the end, it's more like a kitty roaring than like the actual big cat that we would like it to be. It doesn't provide very strong constraints. And the reason it doesn't, it's because the statement just tells us that in the full theory there cannot be a global symmetry, but it doesn't tell us how strongly the breaking can be. It can happen perhaps at some energy scale very much in the UV, which is irrelevant for the two derivative action of the low energy effective field theory. Now, there's been some interesting progress in this direction recently. So some people are trying to pinpoint exactly at which energy scale and which width strength the symmetry breaking effects have to appear. But in this talk, I will take a different approach and tell you how, in a different way, global symmetries can actually give you, just the no global symmetries conjecture can give you very strong constraints on the low energy effective field theory. Okay. So I'm just going to give you right away the gist of the talk. That just the idea is going to be in this slide, and then you can, if you're just going to take one message, it's just the message in this slide. I should mention that this is work to appear soon with Coulomb. So the gist of the talk is the following: the no global symmetries conjecture, and more particularly a version of it, which is the vanishing Cobordism group conjecture of McNamara and Baffa, which I will be reviewing later on, together with anomaly cancellation, just your old standard anomaly cancellation you should always demand for any consistent field theory, is enough to put effective field theories in the Swampland. Okay, so that is the take-home message. That is the thing that you can take home and use in your own effective field theories. That's the basic idea. And I should point out that this is not the first time that this idea happens. In fact, this has been used by Coulomb, Huri, Sheldon Katz, Hichel Kim, and Gary in a series of papers to do more or less the same thing, to upgrade in this case, the completeness principle to full Swampland constraints of low energy supergravity. So that's the idea, and this is the plan of the talk. I will first review the Cobordism conjecture. I will tell you what it is and how this is applied, and I will explain how the Cobordism conjecture requires that we have certain objects in the effective field theory. And I will apply this to 8 and 90 theories with 16 supercharges, where the Cobordism conjecture will predict the existence of certain objects, which we call I-folds. Generally, they are not that fancy. They are in known examples. They are just orientifolds or orbifolds. But the point is that due to the Cobordism conjecture, they always have to be there. And we'll see how they can give us constraints on the gauge group on the 8D and 90 theories, to the point that on a generic point in the Coulomb branch, we can actually claim string universality, that every consistent low energy effective field theory actually arises from string theory. So I will also mention how this can be used to constrain 7-dimensional theories, and then I will conclude. So that's the plan. But before I go on, very important point, please interrupt me. I don't see your face. I don't see if the message is getting across or whatever. So please interrupt me at any point during the talk with questions or comments, okay? I will be pausing for questions, but please just interrupt me at any point, okay? Good. So let's start by talking about the Cobordism conjecture. So what is the Cobordism conjecture? Well, Cobordism conjecture is just, in a sense, it's applying the no global symmetries conjecture to symmetries which are of a topological character. Now, we are used to topological symmetries in field theory. Whenever you have a semi-classical theory, which has some configuration space, and this configuration space has non-trivial topology, you can construct topological charges, charges that do not have another current that arises, from just another procedure in the Lagrangian, but that are nevertheless conserved just by topological reasons. And one example, for instance, is just monopole charge, right? If you have a U1 gauge theory, the monopole charge is conserved, and it's conserved by topological reasons, just because there's a gauge bundle and the first term class, you cannot deform it away. Okay? So these symmetries, they're global symmetries that must also be broken in a theory of gravity. And when you put it like this, I guess it's not too surprising that in a theory with dynamical gravity, just like we have here topological symmetries involving a gauge bundle, in a theory with dynamical gravity, we can have topological symmetries which just involve the geometry. Okay? So as an example, let's just take 5D gravity. Let's just take a favorite 5-dimensional theory of gravity. Could be a compactification of string theory to 5 dimensions. And let's look at it on a t=0 slice. Okay, so we just have t equals, so this is just the t=0 slice. So this is a 4-dimensional space. Now, in a field theory, I can just consider excitations over this flat background. But in a theory of gravity, where the background itself is dynamical, I can do something like this. I can just take a K3, it's a 4-dimensional manifold, and I can glue it to the 5D slice like this. That's something I can do. It's just topology changing transitions, which we expect to have in gravity. And from the point of view of a 5D observer just sitting here in the bulk, this thing looks like a particle. It's localized somewhere. And you can only see that it's a K3 if you get close enough to go down the rabbit hole. From the point of view of a faraway observer, this is just a new particle. And the point is that this, just like the monopole charge, this particle carries a topological charge, which is given by the integral of trace of r squared over the K3. Now, this charge is conserved in gravity. And, well, it's clearly conserved under small deformations. This is a topological quantity, so if I just deform the K3 a little bit, it won't change. But actually, as I just mentioned, in gravity, we have more processes that are not just small deformations of a geometry. We also have topology changing transitions. So you could imagine that you have a situation where your K3, you should interpret this picture as a movie. This is going from right to left. So you start with K3, and it's going to undergo some topological transition. So there's going to be some holes that nucleate. So you should imagine the time is going from right to left. So it could be that some baby universes split off and join back and whatever. And by the time this process is over, we might end up with a manifold with a completely different topology. So for instance, different homology groups. And this is an allowed process. Typically, we would expect this kind of thing to be an allowed process in quantum gravity. A more mathematical way of describing this process is to say that the manifold K3 and whatever else it transitions to, together, they are the boundary of some 5-dimensional manifold P5. And the term that we use for that is to say that the two manifolds together are in the same Cobordism class. You can partition manifolds into equivalence classes where two manifolds are equivalent if they are related by this thing. By this kind of, if the two of them are in the boundary of some manifold. So that structure defines some groups, some abelian groups, on the set of these equivalence classes, which are the Cobordism groups. These are called the Cobordism groups. So for instance, in this particular case, if we want the K3 to also have a spin structure, the relevant Cobordism group is the 4-dimensional spin Cobordism group. And the point of this is that this topological charge that we were describing before, the first Pontryagin class of K3, the integral of the first Pontryagin class, is actually not just a topological invariant, it's a Cobordism invariant. So it's a well-defined charge even when you allow for this topology change in transition in quantum gravity. And in fact, this charge, the pondering class is in one-to-one correspondence to the Cobordism classes in this group. So you could say that whenever you have a Cobordism group that is non-vanishing, you have something like this. You have a global symmetry in your theory of gravity. There could be more general Cobordism groups. Not all of them have to be like this. So for instance, there's another one. This one is relevant for theories with which you can put in non-orientable manifolds. And the symmetry in this case is just a discrete symmetry, so discrete global symmetry, but we would also like it to go in quantum gravity. Okay, so questions about the Cobordism perspective on global symmetries? Okay, so that's the idea. So if you have a Cobordism group like this, there's a global symmetry in gravity, but we don't want to have global symmetry in gravity. So the theory must be doing something to kill this class. So in other words, if we have this K3, somehow there should be some allowed process. It cannot be a smooth topology change in the low energy effective field theory, as allowing for topology change as we just described, but there must be some process in the theory that allows the K3 to shrink to a point. In a sense, if it shrinks to a point, the pondering class of this thing is basically zero, or a sphere or whatever. You would say that the global charge associated to this K3 is it's not conserved. It's basically being destroyed by this process. So the statement that there are no global symmetries in quantum gravity suggests very strongly that, well, first of all, you could phrase this as saying that the full Cobordism group of the quantum gravity theory, including branes and non-geometric configurations and whatever you have it, including these objects here, has to be zero, which is precisely what Coulomb and Jake conjecture. And the point for us is that from the point of view of a supergravity guy, what this is telling you is that to kill this global symmetry, you must introduce these defects. You must introduce these new objects, which are not part of the supergravity, but must be there to ensure that the class is killed. And once you introduce these objects, that you argue, so the point is that, so of course, whenever we do this in string theory, we know that those objects are there. We can construct them explicitly. They're often objects that we've known since the 80s. The whole point of these arguments is to argue that these things actually must happen in general if we are to avoid having a global symmetry. And the key fact here is that these defects can have an anomaly. So if it happens that the Cobordism perspective predicts an anomalous object, and there's no way we can cancel this anomaly, then the theory we started with has to be in the Swampland, because it either has a global symmetry and it has in the Swampland, or it has an anomaly and then it's just an inconsistent theory. Okay? So that is the basic idea that we're going to pursue here. And we're going to use it to get new constraints on the space of theories with 16 supercharges in 9, 8, and 7 dimensions. Okay? Questions so far? Okay, let's get going then. So I want to apply this to theories with 16 supercharges in high dimensions. So I'm going to start by reviewing for you a little bit what we know about those. So 16 supercharges is a lot of supersymmetry. And these theories are actually quite simple. To specify a low energy EFT, a low energy supergravity, there's just two ingredients that we can use. There's just the gravity multiplet, and we can just have one of those, of course. And we can also have a number of gauge multiplets. So the gravity includes the metric, some vector, some two-form tensor, and the dilaton. And the gauge multiplets include a gauge field and a number of scalars. Okay? So that is the field content. Not just the field content, but also the interactions at the derivative level are completely fixed by supersymmetry. And so this theory is pretty much fixed. The only thing that we can do, that we can control, is that we can give a vec to the scalars, which live in a moduli space. And we even know exactly the geometry of the moduli space. It's locally just this thing. Globally, it's a quotient of this thing. It's an Orion moduli space. Okay? So that is the setup. And if one goes to so what can happen in this moduli space? What is the phenomenology of this moduli space? So if you're at a generic point in the moduli space, the gauge group is broken to U1. So it's broken to U1 to some number R, which is basically the number of vector multiplies that you put in your theory, plus some vectors plus the contribution coming from the vectors from the gravity multiplies, which I will be ignoring here. So you can have that. That's what you have in the generic point of moduli space. And at some particular points in the moduli space, it can happen that the symmetry gets enhanced. It can happen that some massive states that you're not seeing in the supergravity actually become massless and enhance the gauge group to something non-abelian, in which case the gauge bosons must necessarily be in the adjoint representation. Okay, so that means that if you want to specify a low energy EFT, a supergravity, in 7, 8, 9, or 10 dimensions, you just need to specify a couple things. You just need to specify the rank of the gauge group, and you need to tell me which possible Lie algebras, because the gauge bosons are in the adjoint, the supergravity only cares about the algebra, not the full gauge group. So you just need to tell me which gauge groups can arise at special points in moduli space, okay? That is all the data that you need to specify a supergravity theory. And so that means that the Swampland in 8, 9, 10 dimensions, it's a very simple thing. We just need to figure out which combinations of rank and Lie algebra are consistent in quantum gravity and which ones are not. So let me give you an example, which of course is you're familiar with, which is the situation in 10 dimensions. In 10 dimensions, there's no moduli space, and there's basically just 4 possibilities. You can have E8 times E8, spin 32 over Z2, and these other 2 guys. So these are the only possibilities which are consistent with anomaly cancellation. And in this particular case, we actually know that the last 2 are in the Swampland. There is a nice argument by Watt and friends, and more recently, studying by imposing completeness and studying anomalies on a BPS string. There's an argument by Hitchell, Gary, and Coulomb, showing that these 2 theories are not in the Swampland. Now, these 2, of course, are the ones that are not in the Swampland, the ones that we know how to get in string theory. So in 10 dimensions, the situation is that everything consistent we can get from string theory, and everything that we cannot get is inconsistent. So there is a string universality. Every consistent low energy effective field theory of gravity with 16 supercharges in 10 dimensions can be UV completed to a string theory. This is the end game for a string compactification, for string theory. Basically, you just argue that with this many supercharges, everything that you can have at that dimension is everything that can be there. The goal is to keep going down and being able to see whether or not we have string universality at lower dimensions. So let's go one step down. So by the way, before I go on, any questions about this? Okay. So let's just look at a generic point in the Coulomb branch. Okay, so let's go back, let's go down 1 dimension. Let's go to 9 dimensions. Let's look at the generic point in the Coulomb branch. And if I go to a generic point in the Coulomb branch where there's no symmetry enhancement, then I forget about the choice of the algebra, and the only piece of data that I need to provide is the rank of the gauge group. So the Swampland is just, so the landscape of possible effective field theories in the Swampland is just a number. It's just which possible values of the number can be realized in string theory, which ones are inconsistent, so on and so forth. So what constraints do we have in the rank? There's a nice paper by Hitchell, Huri, and Coulomb that argues from a strong version of the Swampland distance conjecture and involved with duality that the rank of a theory with 16 supercharges in D dimensions has to be lower than 26 minus D, which is pretty useful because it limits the possible landscape, it limits the landscape of possibilities to a finite set. So here's the landscape in 9, 8, and 7 dimensions. That's all that could possibly exist. So from our point of view, you might have guessed, just every value of like rank 5 theory should exist. Why not, right? There's nothing wrong with that. And then you go and ask, oh, sorry, is there a question? No? Yes? Okay. Well, if there's a question, just interrupt me. So you go to, so then you ask okay, fine, which values of these things can actually be realized in string theory? And the answer is that in 9 dimensions, we only know how to realize rank 1, rank 9, rank 17. In 8 dimensions, we only know how to realize rank 2, rank 10, and rank 18. And in 7 dimensions, there's a few more possibilities. Oh, I think I forgot to circle 13 here as well, but there's a few more possibilities. By the way, these 3 guys are just dimensional reductions of each other, of course. So you see that there's a huge gap between we can argue must be in the Swampland and what you get in string theory. You cannot explain all these guys. And the point of this talk is that we can explain this modulo 8 periodicity. We can explain why the only ranks that you can get in string theory are 1, 9, and 19 by using the Cobordism conjecture and anomalies. Okay? So that's what I will be doing. So of course, I'm not gonna get something out of nothing. You need to put in some assumptions. So I'm gonna give you now 4 facts and an assumption. Okay? Fact number 1. If you look at the 9D and 8D supergravity theories, you just look at the Lagrangian, they admit a parity symmetry, which acts in a certain way on the fields. And this parity symmetry works anywhere in the Coulomb branch. Okay? Now, once you specify the action of bosons, the action on fermions is fixed by supersymmetry, and the only possibility is that it squares to -1 on fermions. So it provides what people call a pin minus structure. Never mind, it's just the statement that this symmetry squares to -1 on fermions. Fact number 3, the fact that you have a supersymmetry, that you have a symmetry of the low energy effective Lagrangian doesn't mean that you have a symmetry of the full theory of gravity. But in fact, this thing is an exact symmetry of all string compactifications that we know of. Okay, so in all of these, of all the string compactifications, this parity symmetry is an exact symmetry of the theory. And how do we know that? Well, there's another fact, which is that if a theory has an exact pin minus symmetry, theory of gravity has an exact pin minus symmetry, that means that parity is gauged and means the theory can be consistently put on non-orientable manifolds, which is the case for all theories in 9 dimensions. So motivated by these 4 facts, we get an assumption. The assumption that we get, that we make, is that in fact this thing is general. We're assuming that every n equals 1 theory in 8 or 9 dimensions should make sense on non-orientable manifolds. Okay? We haven't been able to prove this from more basic principles, like maybe it follows from the global structure of the supergroup or something like this. I would like to think more about this, but right now it's just an assumption, okay? So questions about this? Okay. So this is the assumption, and as we'll see, this assumption has very nice consequences. So if the theory makes sense on pin minus manifolds, we can put it in particular on the real projective plane. That's a pin minus manifold, so we can put the theory there. And it turns out that by saying that the theory makes sense on pin minus manifolds, we have actually introduced a Cobordism group. Because in which RP2 is charged, there's a non-trivial Cobordism group which carries a Z8 charge. So this is a Z8, it's a discrete 8-fold symmetry charge, and this RP2 is charged under it. So the Cobordism conjecture predicts that we should have defects that can cancel this anomaly. Sorry, that can cancel that can allow RP2 to end. And locally, the only possibility is that they look like a quotient of R3 over Z2. So it's just basically the kind of quotient that you do when you take an orbifold or an orientifold. And in fact, this is what they are. If you go to string theory and you ask, do these objects exist in non-examples? They always do. In type 1 prime, for instance, it's an O6 stretching between the 2 O8s. In heterotic models, it's a kind of orbifold. So they always exist. There are orbifolds or orientifolds, and the one thing they always have in common is they involve an inversion symmetry. So we call them I-folds for inversion symmetry. And the whole point is that if there was a quantum theory of gravity in 9 dimensions with rank 5, it would still need to have the I-folds. Okay? That's the key point. We argue that these I-folds must exist. So if the I-folds exist, that means that I can do an I-fold compactification. And in particular, I can put the 9D theory on T3 modulo Z2. That's just 8 I-folds glued together, which are sitting at the fixed points of the torus action. So the Z2 action just inverts the coordinates of the torus. And of course, even we can argue that we have I-folds but we don't know anything about their spectrum. We assume they're supersymmetric, but we don't know how many hypers, how many tensors, how many, we don't know how many, what is the spectrum of the object. However, one can argue, although I don't have time to do it in detail, that when you compactify on a manifold like this, each fixed point is exactly the same. So there's 8 of those and they all contribute the same. So when you compactify on this manifold, this breaks, on this I-fold background, you get a 6D theory. And you break from 6D, this thing kills 8 supercharges, so you end up with a 6D 1,0 model. And a 6D 1,0 model can have an anomaly. In particular, it has a gravitational anomaly that must be cancelled. And so the constraint is that this constraint on a number of tensors, hypers, and vectors. And the whole point is that for us, these 3 guys, they can either come from the I-folds, in which case there's a multiple of 8 of them. Why do we know there's a multiple of 8 of them? Because each fixed point contributes the same. Again, I can talk about this in more detail if I'm prompted. So from the fixed points, you get a multiple of 8 of these guys, multiple of 8 of these guys, multiple of 8 of these guys. But from the supergravity fields, you just can compute exactly how many hypers and tensors you get. And once you feed that into the anomaly cancellation condition and reduce modulo 8, you get the constraint that the rank of the gauge group has to be 1, 9, or 17, which are precisely the values which are realized in 9 dimensions. So with this, we can explain, basically by assuming that the theory makes sense on non-orientable manifolds, we explain the periodicity in the rank that you observe in string theories, and we furthermore argue that there can be nothing else. In other words, we argue that there is Coulomb branch string universality in 9 dimensions. The theory, the most general effective field theory, which is consistent, which can be consistently coupled to gravity in 9 dimensions, are the ones that you can get in string theory at a generic point in the Coulomb branch. We can actually do the same thing in 8 dimensions. So we can compactify on the same I-fold background, and sorry, this is a typo. You get a 5D theory in this time. And 5D theories don't have gravitational anomalies. But this theory must make sense on non-orientable manifolds, as I just explained. And there's a modulo 16 parity anomaly in 5 dimensions. And you can basically play the same game. The I-folds contribute a quantity of the anomaly to that parity anomaly, which is a multiple of 8. And you can compute how much the supergravity fields contribute. And in the end, you get the constraint that the rank is basically 2 modulo 8, which is again the periodicity that we got in 8 dimensions. So it also explains, it also gives you Coulomb branch string universality in 8 dimensions. Okay. There's a subtlety here. You pay a price for the fact that you went down 1 dimension, and instead of super robust local gravitational anomalies, you have this parity anomaly. There's the possibility of a topological Green-Schwarz mechanism. There could be some topological field theory, which we don't see because it has no local propagating degrees of freedom, that cancels the anomaly. We have not been able, so this is something that can happen in principle. We haven't been able to find a theory, a topological theory that would cancel the anomaly. We haven't been able to prove that such a theory doesn't exist either. And I will just say in any case that I don't know of any examples of the topological Green-Schwarz mechanism in gravity. And it sounds kind of fishy to say that you have a topological theory without local degrees of freedom in gravity. So maybe that's not something that can happen in gravity either. But yeah, that's just a subtlety that one has to keep in mind in the 8D case. So with 7 dimensions, we run out of luck. If you do the argument, you can compactify on the I-fold background to 4 dimensions, you don't get a new constraint. One thing you can do though is compactify on an interval, and then you get with similar arguments, and you get that the rank is 1 modulo 2. So we don't explain the pattern, the weird pattern in 7 dimensions, which would be quite amazing. But we at least explain that all the numbers there are odd. So we explain why there's no even numbers. Okay, so pretty quickly, I will tell you a little bit about what can happen about the other parts. The only thing that we are missing to be able to claim string universality, which is what happens to the gauge algebra or the gauge group. So which gauge algebras can be realized at points of enhanced symmetry in string theory, and which ones are in the Swampland? The ones I just circled in red can be realized in string theory. The rest, we don't know how to realize. And there was a nice paper a few years ago, which argued that these guys cannot possibly be realized ever because they have a global gauge anomaly that cannot be canceled by a Green-Schwarz mechanism. So they're inconsistent as field theories already. So that leaves us with two cases: symplectic groups in 9 dimensions and G2 in 8 and 9 dimensions. And right now we're working hard to try and see if we can get at these guys using IFOLs as well. And we'll see if that's possible or not. In any case, one thing that we can do, that we have done with the constraints that we have already, is to provide constraints on the global form of the gauge group in 9 dimensions. This is not really a Swampland constraint in a sense that the global form of the gauge group, it's about the weight lattice where the states live. It's not something that you can see with low energy supergravity, but it's interesting to argue which lattices can arise in string theory and which ones cannot. So it's a constraint on the theory, it's just not a low energy constraint. So by basically applying the same arguments that we have, rather than to parity, to a combination of parity and a gauge transformation on the Weyl group, we can argue that for groups that only have real representations, then the dimension plus the rank has to be a multiple of 8 for the theory not to be in the Swampland, to avoid an anomaly in the Eiffel case. And when you go through all the cases, you get that the cases that I put here in red are ruled out. And indeed, we know no way of constructing any of these in the 9D moduli, in any branch of the 9D moduli space that I know of. Notice again that this is not ruling out any particular Lie algebra, it's just ruling out global forms of the gauge group, okay? So for instance, E6 is okay, but E6 over Z3, which will only have real representations, is not, and so on and so forth, okay? So just to wrap up, basic idea here is that Cobordism plus anomalies can give you Swampland constraints. So it's a good place to look at. It's an efficient way, it's an efficient tool that we can mine to get new constraints. We've used it to establish Coulomb branch string universality in 8 and 9 dimensions. So anything you can get a generic point in the Coulomb branch is what you get from string theory. And of course, the outlook here is to apply these ideas to models with less supersymmetry. So we started with 16 supercharges. The next natural step is to go to 8, where we can actually get some constraints on some infinite families. We cannot completely rule them out, but we can get constraints on some infinite families of 1,0 models. And since we went from 16 to 8, we might as well go all the way to 0 supercharges and ask what happens if you apply these kind of ideas, for instance, to the standard model. So with that, I'm done. Thanks a lot.
All right, thanks for the very nice talk, Miguel. It looks like our first question is from Gary.
Mm-hmm.
Hi.
Hi, Gary.
Hi, very nice talk.
Thanks.
So does your result apply to massive 2A supergravity as well? In particular, the assumption about the existence of the IFOs, is that clear that
the existence of the IFOs? So you're asking if massive type 2A makes sense on pin minus manifolds? That's what you're asking, basically. So the claim would be that if the answer is yes, that you can put in unorientable manifolds of pin minus type, then there is an IFOL there. It is. I'm not sure. I don't think that's true in general. And I'm going out on a limb here. But for instance, it's not true that M theory, just any M theory background, you can put on a or type 2A background, you can put on a pin plus, on a pin minus manifold. You can actually put them on pin plus manifolds. But maybe particular compactifications of massive supergravity, you can argue that this is the case.
Right. You know, what's the next question that I'm going to ask? So some of us are suspecting that massive 2A supergravity with a lot of fluxes and oriented folds are somehow inconsistent. And I was wondering if the line of argument that you're presenting can help us see the problems.
I don't know. I don't see any obvious way right now, but I think that's definitely something to think more about. So the point is that in all these compactifications, we think we know what the local ingredients are. So we know what the anomalies are. So if there was an anomaly, I guess we would have seen local anomalies, but maybe more discrete things like parity anomalies and so on might have eluded us. I don't know. But it's certainly a good direction to pursue, I think.
Okay, thank you. Very nice.
Okay, our next question is from Naomi.
I know.
Hi. I was just wondering, in theories with less supersymmetry, like you were alluding to on the last slide, would you expect these kinds of ideas to constrain more than just the ranks of the gauge groups and stuff? Like what would you be hoping to say with these
So
ideas?
I don't know. I don't know what they can constrain in general. I can tell you a little bit more about this example. So for instance, there's Watty had this paper about so how in 6D supergravity, if you just have theories with U1s, it's kind of easy to find solutions to the anomaly cancellation conditions, and you can have like infinite families. Okay, so that's an infinite family. And it's not just the rank of the gauge group because it's a 6D theory. So it's like there's this number of hypers, there's this number of vectors. I don't know if it has. I don't know how many tensors it has. But so, for instance, we can rule out subfamilies of those families. So it's still pretty. So one thing that I know already that we can do, we can use this kind of ideas. Not with. By the way, I apply it to parity symmetries, but this works with any symmetry you might have in your theory that will lead to a Cobordism group. So for instance, using some Cobordism, using that you get typically a Z2 symmetry in 6 dimensions, which comes from just reversal of the fiber in F theory. If you assume that thing exists, you can kill an infinite subfamily of the infinite families in Watty's example. Unfortunately, an infinite number of guys remain. So it's not like you kill that family or whatever. But I think that illustrates, we're just only starting to apply these ideas. I think you just need to go out and see what we can do with them.
All right, our next question is from Paul.
Okay, nice talk. Hey, yeah, I was just wondering if you, so in which way you have like some I don't know, brain or defect interpretation of this, like in the 9D heterotic context, for example, if this would be interpretable as like a CHL kind of orbifold or brain or something like this, or like for example in 8D, if this could be something like an 07 minus or plus brain or something like this.
Yes, exactly. So that's the point. In non-string compactifications, these I-folds are just objects that we know already. We're not predicting any new objects in string compactifications. Yeah. So for instance, if you go to heterotic, this is a valid worship orbifold that you can take, right? You basically just take a heterotic orbifold with an action including charge conjugation of the internal gauge group, which is always a symmetry in E8 and SOS32, so you can always do this. For instance, if you want to look at the 9D theory from the type 1 perspective, so in type 1 you got the 08 and the other 08 and the brains moving in between. This guy is an 06 stretching between the two 08s.
Right.
So that is something that's the guy in that particular case. So actually, yeah, indeed, these are not new objects. Yeah, and you were asking about the CHL string. So one of the 3D, one of the 8D and 9D. So the theory with rank n, with rank 9, the component of the moduli space with rank 9, that's the CHL string itself.
Right.
And there's the I-fold has different descriptions in different parts of the moduli space. There's one part which looks more heterotic, the one that you get just by flipping the two E8s in heterotic. Then it's just an orbifold as I just described. And you can also describe this part of the moduli space as type 2A with an 08 minus, 8 D8 brains, and an 08 0 plane. And in that case, it's again an 06. So, yeah.
Mm-hmm. Okay, great, thanks.
Thank you.
I think we have time for one more question from Ben.
Hi, Miguel. Thanks.
Hey, Ben.
Talk.
Thanks.
Just a simple question. Did you think about applying your same construction in lower dimensions, say 6 or 5D?
Yeah, well, yeah, that's what this is about, right? Like
I mean, I just with the same number of supersymmetries, not really.
I see. No, at least I didn't think about it in detail. No. So some of the things that we're trying to, so what we're spending a lot of time now with is trying to kill these two guys. So for that, it's sometimes useful to first compactify to 4 dimensions or something. But we're not thinking of the 4-dimensional theories by themselves.
I was just thinking that two-dimensional theories also have constraining local anomalies, so I didn't know if that might.
That's very right. Indeed, that's very right. So maybe you can get something going from 5 dimensions in this case, right? 5 dimensions.
Yeah, maybe.
And that's a great point. Yeah.
But for four-dimensional theories, I basically have no gaps almost. You get all the gauge rank, almost all of them, I think, if I'm not mistaken.
Mm-hmm.
So like the construction in string theory has an upper bound and the rank is derived already, but it doesn't have any. I think there might be a gap of 1 unit or something similar to some of the examples that Miguel talked about in the case of 70, but basically there's not going to be a mod periodicity conditions, mod 1.
Mm-hmm.
Sorry, Kermit, did you mean in 60 there are no gaps, or?
No, I'm saying in 4D, for example.
Right. So I was asking about maybe five dimensions.
I think 4D, I know there's no gap. And I think, I don't know if it started having no gaps in 5D or 4D or what, but it's near there, it begins to have no meaning. I think it might already be in 60. I just don't remember whether there was or not. So I think either 60 or 5D, there's no gap.
Okay, thanks.
Okay, and with that, a big thanks to both of our speakers again for giving such great talks. And next week, we'll have Nikhil Raghuram and Stefano Andriolo speaking. And I hope to see you all there. Thanks a lot.